increasing and decreasing functions. Here, we will use differentiation to find out whether a function is increasing or decreasing or none. Consider the function f given by fx equals to x square, where x belongs to R. Let's make a chart of this function with different values, as shown in the following table. And then let's draw the graph of y equals to x square using the values in the table. We see that the graph of this function is a parabola. First, consider the graph to the right of the origin. Observe that as we move from the left to the right along the graph, the height of the graph continuously increases. For this reason, the function is said to be increasing for the real numbers x greater than 0. Now consider the graph to the left of the origin and observe that as we move from the left to the right along the graph, the height of the graph continuously decreases. Consequently, the function is said to be decreasing for the real numbers x less than 0. We shall now give the analytical definitions for a function which is increasing or decreasing in an interval. Definition 1. Let I be an open interval containing the domain of a real valued function f, and let x1 and x2 be any 2 points on I. Then f is said to be increasing on I if for x1 less than x2 in I, fx1 is less than equal to fx2 for all x1 and x2 belonging to I. Let's take an example. Suppose fx is defined as x for x greater than 0 less than equal to 1, 1 for x greater than 1 and less than equal to 2, and x minus 1 for x greater than 2. The solution: the graph of the function is drawn and we can clearly see for as 1.5 is less than 1.7, f of 1.5 is equal to f of 1.7, and for 2 less than 3, f of 2 is less than f of 3. So fx is an increasing function. Let's learn about strictly increasing functions. Let I be an open interval contained in the domain of a real valued function f, and let x1 and x2 be any 2 points on I. Then f is said to be strictly increasing on I if for x1 less than x2, fx1 is less than fx2 for all x1, x2 belonging to I. Let's take an example. F is said to be strictly increasing in the interval I if x1 less than x2, fx1 is less than fx2 for all x1, x2 belonging to I. Let's see the solution. Consider fx equals to 2x plus 3 for all x belonging to R, and let x1 less than x2. Now multiplying 2 on both sides, we get 2x1 less than 2x2. Again, adding 3 on both sides, we get 2x1 plus 3 is less than 2x2 plus 3. Now we can replace both 2x1 plus 3 with fx1 and 2x2 plus 3 with fx2. So we can clearly see that fx1 is less than fx2. So fx is a strictly increasing function. Let's learn about decreasing functions. Let I be an open interval contained in the domain of a real valued function f, and let x1 and x2 be any 2 points on I. Then f is said to be decreasing on I if for x1 less than x2, fx1 is greater than equal to fx2 for all x1, x2 belonging to I. Now you can see the example of a decreasing function in the following graph. Let's take an example. Fx is said to be decreasing function if for x1, x2 belonging to I and x1 less than x2, f(x1) is greater than equal to f(x2). Here, fx is equal to 1 minus x for x greater than 0 and less than 1. It is equal to 0 for x greater than equal to 1 and less than 2. And it is equal to 2 minus x for x greater than equal to 2. So clearly from the graph, you can see that fx is a decreasing function. Let's learn about strictly decreasing functions. Let I be an open interval contained in the domain of a real valued function f, and let x1 and x2 be any two points on I. Then f is said to be strictly decreasing on I if for x1 less than x2 in I, f of x1 is greater than f of x2 for all x1 and x2 belonging to I. The following is an example of neither increasing nor a decreasing function. We shall now define when a function is increasing or decreasing at a point. Definition 2. Let x0 be a point in the domain of definition of a real valued function f. Then f is said to be increasing, strictly increasing, decreasing, or strictly decreasing at x0 if there exists an open interval I containing x0 such that f is increasing, strictly increasing, decreasing, or strictly decreasing respectively in I. Let us clarify this definition for the case of increasing function. A function f is said to be increasing at x0 if there exists an interval I equal to x0 minus h, x0 plus h for h greater than 0 such that x1 and x2 belongs to I. For x1 less than x2 in I, f of x1 is less than equal to f of x2. Similarly, the other cases can also be clarified. Let's take an example. Show that the function given by fx equals to 7x minus 3 is strictly increasing on R. Solution. Let x1 and x2 be any two numbers in R. Then x1 less than x2. Multiplying 7 on both sides, we get 7x1 is less than 7x2. Subtracting 3 from both sides, we get 7x1 minus 3 is less than 7x2 minus 3. Replacing both sides with fx1 and fx2, we get fx1 is less than fx2. Thus, by definition number 1, it follows that f is strictly increasing on R. Note that let I be an open interval contained in the domain of a real valued function f. Then f is said to be number 1. Increasing on I if for x1 less than x2 in I, f of x1 is less than equal to f of x2 for all x1 and x2 belonging to I. Number 2. Strictly increasing on I for x1 less than x2, f of x1 is less than f of x2 for all x1 and x2 belonging to I. Number 3. Decreasing on I if for x1 less than x2 in I, f of x1 is greater than equal to f of x2 for all x1 and x2 belonging to I. And number 4. Strictly decreasing on I if for x1 less than x2 in I, f of x1 is greater than f of x2 for all x1 and x2 belonging to I. We shall now give the first derivative test for increasing and decreasing functions. The proof of this test requires the mean value theorem studied in continuity and differentiability chapter. Theorem 1. Let f be continuous on a and b closed interval and differentiable on the open interval a, b. Then number A, f is increasing in closed interval a comma b if f dash x is greater than 0 for each x belonging to open interval a comma b. Number B, f is decreasing in closed interval a comma b if f dash x is less than 0 for each x belonging to open interval a comma b. C, f is a constant function in closed interval a comma b if f dash x is equal to 0 for each x belonging to open interval a comma b. Now you can click on the proof button to get the proof of number A. Theorem 1. Let f be continuous and closed interval a comma b and differentiable on the open interval a comma b. Then f is increasing in closed interval a comma b if f dash x is greater than 0 for each x belonging to a comma b. Proof. Let x1 comma x2 belongs to closed interval a comma b be such that x1 is less than x2. Then, by mean value theorem, there exists a point C between x1 and x2 such that f of x2 minus f of x1 is equal to f dash c into x2 minus x1. That is, f of x2 minus f of x1 is greater than 0 as f dash c is greater than 0. That is, f of x2 is greater than f of x1. Thus we have, for x1 less than x2, f of x1 is less than f of x2 for all x1 and x2 belonging to closed interval a comma b. Hence, f is an increasing function in closed interval a comma b. The proofs of part B and C are similar. Slope of secant AB is equal to m of AB, that is equal to f of B minus f of A divided by B minus A. There exists some C in open interval a comma b where the slope of tangent equals the slope of secant AB. Let's take an example. Show that the function f given by fx equals to x cube minus 3x square plus 4x for x belonging to R is strictly increasing on R. Solution: f dash x is equal to 3x square minus 6x plus 4. Taking 3 common, we get 3 into x square minus 2x plus 1 plus 1. Now this can be written as 3 into x minus 1 whole square plus 1, which is always greater than 0 in every interval of R. Therefore, the function f is strictly increasing on R. Let us take an example. Find the intervals in which the function f given by fx is equal to sin x plus cos x for x greater than equal to 0 and less than equal to 2 pi is strictly increasing or strictly decreasing. Solution: we have fx equals to sin x plus cos x. Differentiating it with respect to x, we get f dash x equals cos x minus sin x. Now, f dash x equals to 0 gives sin x equals to cos x. which gives that x equals to pi by 4, comma 5 pi by 4, because x is within the closed interval 0, comma 2 pi. The points x equals to pi by 4 and x equals to 5 pi by 4 divide the interval 0, 2 pi into 3 disjoint intervals as shown below. Then f dash x is greater than 0 if x belongs to the shown interval. F is strictly increasing in the interval as shown. Let us take an example. Find the intervals in which the function f given by fx equals to x square minus 4x plus 6 is a. strictly increasing, b. strictly decreasing. Now f dash x is equal to 2x minus 4. Therefore, f dash x equals to 0 gives x equal to 2. Now the point x equal to 2 divides the real line into two disjoint intervals, namely minus infinity to 2 and 2 to infinity. In the interval minus infinity to 2, f dash x is equal to 2x minus 4 is less than 0. Therefore, f is strictly decreasing in this interval. Also, in the interval 2 to infinity, f dash x is greater than 0. So the function f is strictly increasing in that interval.